Hello! Today I want to show you how linear algebra can be used for basic facial recognition. I'm Matt, and I love linear algebra. Let's start with the basics. Any picture on your computer is actually stored as a matrix of numbers. Storing images in these rectangular matrices is really done out of convenience. In the past, it was proposed that we store images in hexagonal grids, but that idea never really caught on. Now there are tons of ways to compress digital images, and each one could easily have a video all on its own. But to keep things simple today, I want to talk about just one method, principal component analysis, or PCA. This method relates directly to linear algebra, and it involves something you may have seen before in a first-year linear algebra class. I'm talking about good old-fashioned eigenvectors. You may have even found some eigenvalues and eigenvectors in the past by taking the determinant of the matrix A minus lambda times the identity matrix, setting this to 0, factoring the characteristic polynomial to get the eigenvalues, then plugging in these eigenvalues and solving the system of equations to find the eigenvectors. Now, a problem comes up when you try to find the eigenvectors of a rectangular matrix, or one that isn't square. You can't take determinants of these matrices, so you can't use the same method to find the eigenvalues. But if you multiply any matrix by its transpose, the result will be square. So what if you find the eigenvalues of the matrix A times its own transpose? It turns out that this is a very useful technique called the singular value decomposition, or SVD. Okay, so we have digital images stored as rectangular matrices, and we have the SVD theorem. The best thing about eigenvectors is that they're mutually orthogonal. That is, the eigenvectors form an orthogonal basis for the vector space that our picture lives in. Now, if you have lots of pictures of the same thing, like faces, then you can use the eigenvectors to capture the variability in your sample. This is usually called principal component analysis, or PCA. Thank you, yes. I got through the paragraph, thank you. Let me show you what PCA looks like in practice with some actual pictures of faces. Alright, so let's do some image recognition with PCA. We're going to use this code, which is from the scikit-learn official documentation. So I'll just get my data loaded in here. These are a lot of images of famous people, so we should recognize some of them when I plot them. Here's George W. Bush. Here we got Tony Blair.
So we have a bunch of people. We're going to use these to generate our eigenfaces. In other words, eigenvectors. So this is going to be doing that, okay? Eigenfaces extracted. This is the classifier, which in our case is an SVM. We really can't talk about these things right now. All right, so now we'll just see how this thing did for predicting. So it projected test faces onto the basis of eigenfaces, and it was able to do some pretty accurate facial recognition here. Looks like we've got Donald Rumsfeld with 95% accuracy. Hugo Chavez was very accurate. Now let's get a look at some of these predictions here. All right, so I did pretty good predicting these faces. That's excellent.
So what do the eigenvectors of faces even look like? Oh, it looks like I lost my output here. Horrific. Now, those ghostly faces represent the variability in our sample, and they are terrifying. So, if you want to recognize a face, and you have at least some version of that face in the sample that generated your eigenvectors, then you can project the face onto the basis of eigenvectors and compare. I hope you learned something new about the applications of linear algebra in this video. And I hope you'll forgive me that I'm sorry that I'm not sorry that I brought up eigenvalues and eigenvectors again. And as always, until next time, keep it linear.